Welcome back, everybody. So we're now going to look at the washer method from 6.2 here, which is going to be the second major method for volumes of solids of revolution. So for the washer method, it's kind of called the washer because it can be represented by what looks like a washer here, right? So a washer is a little metal ring that you typically put when you're bolting or screwing something in, just to create a better seal and to, avoid stripping of the screw itself. And so that's what we're going to be creating essentially, is a solid shape that has some missing volume to it. So note, when we talk about the disk method, this is completely solid, right? So this region is just completely solid, and we have a completely solid figure. But for the washer method, we're going to want to be a little bit more precise because we're going to be missing a section, and we're going to have sort of a hole in our graph. So on the graph below here, we can see the two representations of our solids here. So what we'll note is for that graph in blue, the graph in blue has a hollow portion inside there. So there's a portion there that it's hard from the picture here, but we can see we've got this section is rotated, and we get this symmetric section on the bottom, and then the actual solid itself is going to have a hole in between it. So we get this sort of horn kind of shape to it. So the question is how is this going to differ from the disk method? Well, it's really not going to differ too much other than thinking about how we get that hollowness. So in other words, if we're looking at our two curves here, so we've got y is equal to x and y is equal to x squared. So what we want is we want a solid region here that is rotated about the x-axis. So we're going to take that little sliver and rotate it about the x-axis, which means that if we're using the disk method, we need to somehow get rid of this huge section below it, right? Because if we just rotated the red curve, we would get, a triangular cone. So we don't want that because we don't want all of this section below. We want to delete that out. So what we'll notice is if we took the blue curve's area and we subtracted out its area underneath, that'll leave us with the area between, which we can then rotate to find a volume. So essentially what we're going to do is we're going to apply the disk method to each one of these curves and then subtract the smaller volume. So the washer method is going to involve subtracting volumes. All right, so let's look at how we would set this up. So what we're going to do then is first measure our radii, of course. And note, I say radii because we're going to have two different radius. We're going to have this shorter distance and this longer distance. And so the smaller distance, we're going to use little r of x, and the larger distance, we're going to use capital R of x. And the little r is sometimes called the inner radius. The larger one is sometimes called the outer radius. So what we're going to do then is take the volume, and note for our curve here, it's 0 to 1 of r of x squared. And so to get the volume in between them, we're going to, so this is volume 1, this is going to be of the red line. And then volume 2 is going to be pi integral 0 to 1 of little r of x squared dx. And that's the volume of our curve. So maybe we'll just draw that region kind of like that. For the red, we'll draw our region like that. And all we're going to do is subtract them. So then our volume of our solid is going to equal pi. So note they both have a pi involved in them, but we can maybe write it more explicitly. So 0 to 1, pi r of x squared minus pi r of x squared dx. All right, so we'll just combine the two volumes. We could do two separate integrals and combine the two separate integrals because our limits of integration are the same. So what we're going to end up with then is pi integral 0 to 1 capital R of x squared minus little r of x squared dx. So we just subtract the two separate volumes of our curves, and that will give us our washer volume. Now we still need to interpret the axis we're rotating about, because clearly we're just using a modified version of the disk method. So we'll note horizontal axis is still, rotating about the x-axis or some line y is equal to a number. And then vertical is going to be a y-axis revolution or x equals a number as a line. So what we get for the horizontal case is going to be, again, what we wrote below or above. So the integral from a to b of the outer radius volume minus the inner radius volume, which we can combine into a single integral expression like this. And then for our vertical, it's still going to be the same. But now we're going to be integrating along the y-axis, and we'll have functions of y instead of functions of x. Okay, so this is just going to require us to find both radii and then apply the volume for integral expression. Okay, so let's go ahead and jump right in. So we've got y equals x squared and y equals 4x minus x squared. So we'll note that this is x times 4 minus x, which will make it easier for us to graph. We could start with the intersection points if we wanted to as well. So why don't we do that? So intersection points can be helpful to start with. So when is x squared equal to 4x minus x squared? So that will be, if we subtract the x squared over 4x minus 2x squared, we can factor out a 2x. So it looks like 0 and 2. All right, now let's actually graph this just to see what it looks like. So we've got x squared, and then 4x minus x squared. So that has zeros at 0 and 4. Let's say 4 is over here. We know that they're going to intersect at 2. So that's the parabola that looks like this. And it's, helpful to graph more rather than less. We can see that we don't need that section on the left here because our region, our region is just right here. Okay, so we know the intersection is at 2 and 0, and now we are ready to begin. So we're rotating about the x-axis. So we know that we're rotating it this way. So then our radii are going to be perpendicular to that. So let's go ahead and draw in our 2 radii. So we can see the blue curve is the smaller radius and the red curve is the larger. So maybe we'll put a little r, capital R here. And we'll just note. So r of x is going to be 4x minus x squared, and then little r of x is our blue curve, which is just x squared. All right, so now we've got everything we need for our volume. Now we just need to write it and then work it out. So v is going to equal pi, integral from 0 to 2 of our outer radius squared minus our inner radius squared. All right. And now we need to work this out. So we've got pi integral 0 to 2. So if we multiply this out, let's see what we end up with. We'll have 16x squared minus 8x cubed plus x to the fourth minus x to the fourth. So this is nice because we get some nice cancellation at least. And then we'll have pi, and we can integrate directly here. So we're going to have 16 thirds x cubed minus 2x to the fourth. Yes. From 0 to 2. Luckily, we're evaluating at 0, so we only really need to worry about at 2. So at 2, we'll have 16 times 8, which is going to be 128 over 3 minus 2 times 16, which is 32. And 32, so we'll just note this is going to be 32. 32 is 96 over 3. So what we're going to end up with is 32 over 3, it looks like, times pi. So 10 and 2/3, 32 over 3 times pi. So the setup is really always going to kind of be similar, where we're looking for our radii. Definitely want intersection points. Definitely want our radii kind of explicit, and your graph is going to be really important in the examples where you don't have a calculator. So again, any of these examples that don't say anything are non-calculator. If it says calc OK, you can use your calculator, but it's really going to require you to graph really polynomials and trig functions, some exponential and log functions possibly, but exponential and log functions typically require a calculator because you're going to have messy intersection points. So if you get a graph, the intersection point should be solvable algebraically if it's non-calculator. All right, so we've got a couple more examples here, 5, 6, and 7. So let's go ahead and get started. So we'll just note for number 5, let's focus on what our curves are, which is, the same curve. But now we're going to change what we're rotating about. So we're going to look at it rotated about a different axis of revolution. So let's go ahead and see what this looks like. So let's graph it. So note we know the intersections already. So intersections are x equals 0 and 2. And we can just sketch our graph here. So again, this is that same region. And I'm only going to graph the region. You can sketch a graph of the entire function again if you want to, but we've already done this in the previous example. So we know that's the region that we're interested in, but now our line of revolution, or our axis of revolution, is above our curve at y is equal to 6. So I'll put a big arrow here. So now we're going to be rotating it from y equals 6, which means that when I measure my radii, still perpendicular, but I measure in the opposite direction. So we're kind of measuring oppositely, and we'll see that little r is going to the red curve now, which is that 4x minus x squared, and then capital R is going to our blue curve. So let's take a look at each one of these functions. So r of x, now note we're measuring from above, we're not measuring from 0. So we're measuring from 6, which means we need to do a top minus bottom calculation for each one of these. So capital R is going to be 6 minus our curve, x squared. So you can think of it this way. If this length is 6 and this length is x squared, then the height is going to be 6 minus wherever x squared is located. So it's going to be the difference in height between your axis of revolution and that curve, which means little r of x is going to be 6 minus 4x minus x squared. So now we're changing which radii is outer and which one is inner. We can clean up little r of x a little bit, so that'll become positive x squared minus 4x plus 6, just putting it in standard form. But the only thing that's changed is the radii. and our limits of integration are still the same. We're still between 0 and 2. So now let's see what our integral is going to look like. So our volume is going to be pi, integral from 0 to 2. And now we're going to get this different expression. So we've got 6 minus x squared minus x squared minus 4x plus 6. So we can see that we've got a different expression from our previous example. But let's go ahead and work it out. So we're going to get pi integral 0 to 2. So we'll have 6 minus x squared plus 4x minus 6. So just distributing everything out, we can see that we get some nice cancellation here. And then we can combine the x squareds, it looks like. So we'll have pi integral 0 to 2 of, I'm going to write this as 4x minus 2x squared dx. So then evaluating, we'll get 2x squared minus 2/3 x cubed from 0 to 2. So we'll get pi, and at 2 we'll have 2 times 4, which is 8, minus 2/3 times 8, which is 16 thirds. And it'll be minus 0, so we don't need to worry about the 0. And we'll just note that 8 is 24 thirds, so 24 minus 16 is 8. So we're going to get 8 over 3 times pi. All right, so we can see that if we revolve it about a line that's not the x or y axis, it's going to make our radii a little bit different and a little bit more complicated possibly. So we do need to be careful with our work there. All right, so let's go ahead and move on to number 6. So we want to find the volume of the solid form by revolving the regions bounded by sine and cosine in the first quadrant about the x-axis. So for this one, I think we're going to have to add a domain because sine and cosine intersect each other quite a bit. Whoops. So let's see. So we've got cosine. Oops. And this is a very common example that you'll see. So we want in the first quadrant. So we'll note that both graphs are going to start something like this. So we probably want to be a little bit more specific. So let's do bounded by y equals sine x and y equals cosine x and the y-axis about the x-axis. So we'll note that, this is going to kind of continue on. Kind of like this, but we're only interested in the first quadrant region and the y-axis, which means the only region we really want here is going to be this little sliver on the left. And so I'll try to make sure that I'm very careful on which region it is so it's not kind of unclear. But we're going to have to do a little bit extra work here to figure out, say, our intersection points, etc. sometimes, especially with trig functions. So we'll note we're rotating about the x-axis. And we should look at what our limits of integration are. This one's pretty obvious, right? So sine x equals cosine x. Where do they intersect? Obviously, they're going to intersect at pi over 4 radians. However, if you don't recognize that, we could solve this pretty quickly by, let's say, dividing both sides by cosine. So tan x equals 1. So tangent x is equal to 1 when x equals arctan of 1. In the first quadrant, of course, that first value will be pi over 4. So a little bit of trig that you might have to do here. And then for our regions, we can just draw our radii. So we've got little r and capital R there. So capital R is going to be cosine, and little r is just going to be sine. So then that little region is going to be represented as a volume by pi integral 0 to pi over 4 of cosine squared x minus sine squared x, which again is going to be that familiar integral that we looked at way back when in chapter 4. So if you try to integrate this as is, you can't, because you don't know how to integrate cosine squared or sine squared necessarily. There's a couple of different ways you can do it. We could use half angle identities if we wanted to, but it's really useful to note that this is just equal to cosine 2x, the double angle of cosine. So we can just write this as cosine 2x dx, and then we can evaluate directly. So the integral is going to be 1/2 sine 2x from 0 to pi over 4, which is going to be pi 1/2 sine of 2 times pi over 4 is pi over 2, which is 1, and then minus 1/2 times 0, since sine of 0 is 0. So we're going to get pi over 2. So the volume is just pi over 2. All right, so let's go ahead and look at this last example for washers. So find the volume of the solid formed by revolving the region bounded by y equals x and x squared about the y-axis. All right, so let's go ahead and graph this. So this one's going to be pretty easy to graph. We've got y equals x and y equals x squared. So we're going to get that example that we had previously at the start, but we're revolving around the y-axis now. So we'll note they intersect at 0 and 1. You can solve that pretty easily to find those intersections, but we've already looked at this example also. So then if we look at our radii, what we'll notice is that they need to be functions of y. So we've got little r and capital R, which are perpendicular to our axis of revolution. So r of y and little r of y. Well, let's see. So little r is just y equals x. So we can just call that x equals y. But then the red curve is x squared. So if we're solving for x, we're going to get the square root of y, and it'll be the positive portion since we're in the first quadrant. So this is going to be rad y. And we'll also notice that we're integrating along the y-axis now. So we need to be really careful here and actually double check where is the intersection point of y. And luckily in this case, 1, 1 is the coordinate where they intersect, so it's just 1. But make sure that you recognize we're integrating vertically, or we're integrating along the y-axis as opposed to along the x-axis. All right, so let's go ahead and compute our volume then. So we'll get pi integral 0 to 1 along the y-axis of the outer radius squared minus the inner radius squared. And so that'll just be y minus y squared. And this should be pretty easy to evaluate. So we'll have 1/2 y squared minus 1/3 y cubed from 0 to 1. So we'll have pi 1/2 minus 1/3, which is just going to be 1/6. So we'll get pi over 6 as our answer. And again, we'll get a lot more practice with these but something to be just generally aware of in your work always is just being careful. Be very careful with your work, especially when it gets messier. All right, so that concludes the washer method here. So we've got all of these examples down. So the last part is going to be volumes of known cross-sections, which we'll finish in our next video. So if you have any questions, send me an email. Otherwise, come by the office hours. And